Let's welcome Associate Professor from Nicolaus Copernicus University in Toruń, Ms. Katharina Bogusławski, PhD, who will take us into the world of combined applied informatics and quantum mechanics. Welcome.
Thank you very much for this kind introduction. And first of all, I would like to thank the organizers for inviting me. It is a wonderful meeting. I learned many things, and I heard a lot of inspiring speakers. So I hope I will be inspiring too. So, where are my slides? I need to do this. Okay, thank you very much. So. I'm not directly involved in IT, so I am a scientist. So my talk will be very sciencey. So to be more precise, I'm a theoretical chemist. Yes, theoretical chemist, it does exist. And today I will try to show you how we apply or use applied informatics and combine it with quantum mechanics so that we can design materials on a computer. So, in other words, how we try to make the world a better place using computers. So, before I start, I would like to give you a short overview over my journey, how I joined the IT business or scientific computing. So, everything started actually in this city. So, I was born here in Bydgoszcz, but I was raised in Germany. I spent only 3 years of my life in this town. And at some point there, I decided I want to get an education, and I want to get the best education I can get. And I told my mother, "Ma'am, I'm going to study in Switzerland." And she was like, "Oh God, please don't do that. We don't have the money." And I was saying, "No, don't worry. Everything will be fine." And I did it. So I was still young. I was naive. And I took a risk, a calculated risk. And I went to ETH Zurich, and I studied chemistry. So I did my bachelor and master there. And then I did also my PhD there, but my PhD was in computational chemistry. And this was the first place where I got in contact with scientific programming. And I started with C++ and Fortran, so maybe some people don't know because you're younger what Fortran is, but maybe you're familiar with C++. So I spent 8 years of my time in Switzerland, and then I moved on to do a postdoc, and I moved to Canada. So to Ontario, I joined McMaster University in Hamilton, where I focused completely on theoretical chemistry. And I dived deeper into scientific programming and then 100% into Python. So I spent there approximately 3 years of my life. And then I decided I'm going to move back. And I moved back to Toruń. To NCU, where I started to do quantum physics and quantum chemistry. And we started, as a team, to develop our own software. And this software is written in Python and C++. So it's basically a very long journey. It started here, and it ended like 40 kilometers away from here, approximately. And what we do in my research group is heavily relies on scientific programming. So in a nutshell, what we do are 3 things. So first of all, we do method development. We try to derive mathematical models which allow us to describe electrons so that we can predict better materials, better molecules. So you might have better phones, better TVs. So this is something what we focus on. And the challenge we have here is that we have a really balanced description between cost and accuracy. So the methods we develop, we then try to implement in our own software. So we develop our own software in my group. And this covers all stages of software development, starting from the design, implementation, to the final deployment and maintenance of the software. So finally, we take these 2 pillars. So we have our methods, we have our software, and we model the quantum world. So we basically do so-called large-scale modeling, where we take molecules and we do some calculations on computer and they predict the properties. And some molecules we study, you are familiar with, they are so-called organic electronics. So organic electronics you find on your phone. So you don't have phones like this yet, but probably in the future. TVs, obviously, but also solar cells, where we want to produce green energy. So if you want to have or want to improve such kind of materials, you can do it in the lab during experiments. But this is a very tedious task because it relies heavily on trial and error. You do something, you test it, and maybe you succeed, you don't know. It takes a lot of time, and it takes a lot of resources, so it costs a lot. If we were able to understand the relation between structure and property, we could speed up the design. So we have to answer questions like, how does the molecular structure affect efficiency or stability of our compounds so that we can have better solar cells, for instance? And this is an area where quantum chemistry can help to accelerate the development, so we can efficiently pre-screen some molecules, and we can construct a data set that will allow us to build new materials, like putting Lego blocks on top of each other. So this is the main idea. So if you do it in a lab, you typically design new materials for specific strategies, and this is called ligand modification. So if you have a material, you have one compound which is important, you want to study, which has specific properties. So you pick out that compound in the lab, and you try to modify it. So for instance, take this orange guy here, and you will substitute this so-called ligand, so this molecule, by something else. So you add atoms. So experimentalists, what they do is they have to synthesize it, they extract it, they measure it, the efficiency and the stability of it, and then they decide, is it good, is it bad? If it's bad, and usually it is bad, they start from scratch. So it takes a lot of time. What we do is we can do all these things on one day, basically. So we are much more efficient, and we can handle much more molecules simultaneously. But if you want to do that on a computer, the models you have, they are extremely difficult. And I will show you why. So our starting point is, in order to do it on a computer, we have to solve an equation. And the equation we have to solve, it's a Schrödinger equation. You might not, or you might have heard of it. It looks very simple. So we have an energy. We have our wave function. It's just a function that describes the molecule and everything you want from it. And we have something which we call the Hamiltonian, H. The Hamiltonian, it contains all the interactions between the particles, and in our case, it's electrons and nuclei. So this is one water molecule. It has 10 electrons and 3 nuclei. And for the total energy, what we have to do is to calculate all the energies we have in the system. So we have kinetic and potential energy. So now what we have to do is, if we want to solve this equation, we have to impose approximations, and we impose a lot of them. So the first thing what we do is we say, okay, nuclei, they are heavy, they don't move at all, and we only focus on the electrons. So then we have to solve an equation that looks kind of similar, like this here, but it only is about the electrons. And for those who are interested, this is basically the operator, so what we have to treat. It contains the kinetic energy of the electrons and just some classical charge-charge interactions. So this is our starting point, the equations we have to solve, and we actually know how to solve this equation. We can solve this equation exactly. And I have written down here the exact solution. It looks very complicated, but just focus on this part here. It's just a sum over some functions. So you take one function, you add another one, and you do it until some specific number. And these functions, so the functions in red, they are given. So they are user-defined, they are chosen by the program or whatever, but they are given. And the thing you have to optimize is just a set of numbers. It sounds pretty simple. So these are the unknowns. So for the devil lies in the details. So if you look at the functions, and I've drawn them here using graphs or pictures, it's an easy way to visualize this function. So usually what we do is we have some lines which we call energy levels, and they go up, so each energy level lies above the other one. And then we put electrons in there, so just particles, usually two at most in one of these levels. And this is how we construct these functions. So as I said, the devil lies in the details. If we have a small system, 2 electrons, 2 energy levels. There are 3 degrees of freedom, that means 4 such functions, and we can still store this wave function, right? We can store this problem even on a personal computer. If we go to the water molecule, we have around 10, and we have 10 such energy levels, we have more than 60,000 degrees of freedom. So 60,000 such functions. But these are not interesting systems, even if you consider just 2 molecules. It's not very interesting, 2 water molecules. You have more than 30 billion degrees of freedom. And if you want to store this wave function on a computer, it takes you 300 gigabytes. So you don't have a personal computer that can store this wave function. A realistic system, so a material you want to model on a computer, is around here. So you have like 200 electrons and 1,000 basis functions, so 1,000 energy levels. And the number here I cannot compute because my computer does not calculate such a large number. So it's a gigantic number which we cannot store on any machine, or even if you combine all the machines on this planet, you cannot store it. So what do we need? We need better approximations. We need a better way of parametrizing this guy. And we can do it by just choosing the proper functions here, or trying to find better ways to optimize these numbers. And this is what we are doing, what quantum chemists basically do. And there's always a balance between how expensive it is to get the numbers and how accurate these numbers actually are. And typically, the more expensive your calculation is, the more accurate it will be. So if you want to describe materials, you are usually somewhere in between this region here, around n to the 6th. So n is the number of energy levels you have. If you want bigger ones, you have to go down in computational cost, but also accuracy. For smaller systems, you can go up there. But usually, you should be in this regime. So the methods we develop in my group are actually in this range. And we consider a specific type of methods, which are called coupled cluster methods. So we take one function, and we just act with another function with an exponential, so e2 something, on it. And then we have to solve for the unknowns, which are given here in the exponential. So we construct this function, and we have to optimize numerically some numbers. The problem here is also non-trivial, because it's highly nonlinear. So the equations we have to solve, they are coupled. We have to solve them iteratively. It takes a lot of resources to do that. We need efficient implementations. So the methods usually scale n to the 4th and n to the 6th. And if you want to hear about numbers, it is around a day or a month of computing time. So you run such a calculation, approximately a month, can be longer on a simple computer. And we don't use simple computers. We use so-called supercomputers, where we have terabytes of memory and terabytes of disk space. So if you want to know what the problem actually looks like, what we solve, it's a problem you learn in high school. So the mathematical problem itself is not very difficult, because what we try to do is we find the roots of a function. So the values where the function is basically 0. So if you have x squared, that is trivial, because for x equals 0, then you have already a solution. However, our function looks very, very complicated. I've written it down here. We have a lot of intermediates, so all these letters you see, there are some intermediates. If I would write down the whole equation, it would not fit me on one slide. So this is a very difficult problem numerically. It's nonlinear, as I said. The equations are coupled. And we need very efficient optimization, so efficient algorithms that can actually solve for this kind of problems. And these algorithms, we actually implement ourselves. So in my group, we develop our own software, which we called PyBest. It's a Pythonic black box electronic structure tool. And the development of PyBest involves all stages of software development. So what's very important here is teamwork. We have international and interdisciplinary contributors. So we have contributors from physics, from chemistry, technical physics, applied informatics. Our international dev team currently comprises 5 countries around the globe. So we have people obviously from Poland, but also from from Germany, from Iran, from India, and Algeria. So another important thing is design. So we have an open source code, which is fair. It's supposed to be modular. We want to include as many features as possible, as many different libraries as we can. We want to extend our code to GPU, to support GPUs. And at some point, we are currently working on it. We want a graphical user interface because people who are not experienced with the terminal, we already heard about it, they have problems in actually using it. So a graphical user interface is very useful here. The language we are programming in is Python and C++, but mostly it's Python. Another important part is continuous integration. So those who develop software, they are familiar with it. It is very important that we have continuous quality control. When you develop a software has to be built periodically. It has to be tested automatically using unit tests. We also use version control. We already heard about it, how important it is. And very important is also code review and approval. You cannot just push a code somewhere and let it do whatever. So quality maintenance is important when you develop some software application. We want to apply our code for systems across the periodic table. So we did already main group chemistry, actinide, so the things you find in a nuclear reactor when you generate nuclear energy, lanthanide chemistry, and organic electronics, as I showed you, like solar cells or organic light-emitting diodes. So finally, our code is just one code among many. So there are tens or hundreds of software packages out there that just work in quantum chemistry. So I mentioned here a few. Some of them are open source, but many of them are commercial. So you have to pay big money in order to run them on your computers. They are written in many languages. So again, Fortran, most of them are still written in Fortran. It's a little bit painful for the younger generation, but we are always moving to newer languages like C++ and Python. I think Julia is not that Julia language. It's not coming into quantum chemistry, but in physics it's already used. GPUs are coming as well. It's a little bit difficult in quantum chemistry to have efficient GPU implementations because it's not always useful. I've mentioned also some challenges, current challenges and future challenges. So if you want to study large systems, we need massive parallelization. So you don't run a simulation on one CPU, you run it on 10, hundreds, ideally thousands of CPUs. So this is important and it has to be done efficiently. Automatization, so we want to provide the user with a computational black box. It is also a challenging task. And last but not least, quantum computing is emerging. We can do, if you have quantum computers, even larger systems, which is also a difficult task. So finally, let me acknowledge my group and my coworkers. So we started as a very small team. Basically, it started with the two of us, but many people joined us over the years. So this was the first original developer team of PyBest, and now we have also new members shown here. So personally, this guy here is my husband. So yes, we work together, which is kind of easy. It simplifies our life, especially I have two little kids, so it makes family balance, work-life balance easier. But the important message here is, if you want a family and you want to do science, maybe there's one or two people in this audience who actually decide on a career in science. It's possible, you can do it, and I'm sort of an example that everything is possible. Also, I'm also the leader of this group, so women in IT can be leaders as well. So if you may have noticed here, some people always say to me, I don't recognize you because you changed your hair again. So I have now 3 pictures of me and I changed my haircut again. So maybe next time if we meet each other, I will have a different haircut again. So I have to acknowledge funding agencies, very important, which are written here, and I thank you for listening. And if you have questions, don't hesitate to ask. You can also ask in Polish, so I understand Polish. Thank you.
to help chemists make better decisions, like what to synthesize to get better results?
Yes, so there are some things experimentalists need to know, right? So specific properties of the molecule, which we can calculate, and I told you we can do it in a day, in a week, and this is what they need. So they don't want to sit in the lab and do the synthesis, because it's really, I mean, they really want to screen something. Excuse me?
It takes a lot of time and always doesn't bring the result we want.
Exactly. When the challenge here is to have a theoretical result in reasonable time, so we are sort of also limited with the sizes and the systems and the accuracy. So we started with this. So I cannot tell you how accurate our methods right now are, because I'm not calculating something right now, and the experimentalist told me, I'm not telling you the result. I want to see if your method actually works. So I'm generating right now numbers, and in a week or so, he will tell me if I have good numbers or bad. So I don't know yet.
Maybe I will ask you later on the social media.
Thank you. I think we're right at time. So.